If you want to know how similar two sequences are, you might ask yourself, what is the longest part they have in common? And if you're not asking yourself, I'll ask for you. Imagine you have two words, and you want to find all the ways they look similar, without changing the order of the letters. To begin with, you might not even be looking for the longest contiguous part. As long as the common parts appear in the same order, that could be good enough. These are called longest common subsequences, and finding the longest common subsequence between given strings has many important real-world applications. An interesting problem to start with is finding the length of the longest common subsequence, and this is what you'll learn about in this video. Because meaningless strings of letters are, well, meaningless, let's look at two words we can pronounce. We want to find their common subsequences, such as PI, or NES, or what I believe is the longest PINES. Note that there is not one longest subsequence. You might have found other ways to get that longest word, like this, for example. So how will we approach this? As we do very often in dynamic programming, let's start at the very end. A very good place to start. And the reason it's a good place to start is that it will help us write the recursion. Now here's a spoiler. We'll be looking at the recursive solution for this problem, but only because it will lead us to an iterative solution. The most efficient solutions for this problem in terms of time and space take the bottom-up approaches. Okay, so we'll start by comparing the last letters of the sequences. Either they match or they don't. If they match, that adds 1 to our count. And this suggests one type of subproblem. We found a match, we're on a roll, so let's keep going with the next smaller size of words. We'll take off one letter from the end of each string, and we'll compare these two shortened strings, like this. I moved the last letters off to the side, so you can see the shortened words. So now we have gone down to comparing only the first 8 letters of both words. We took off the last letter of each word, and now we have two words whose last letters do not match. So obviously, we're not going to add anything to our counter. The letters don't match, so they don't count as common substrings. But if you notice, the letter E at the end of Pinecone matches the E in happiness. So if we only compare the last letters, we'll never catch that match. That rhymes. Okay, so here's what we'll do. In the case that the last letters do not match, we'll take turns. First, we'll check the whole of the first word with the prefix of the second word. And then we'll check the other way. We'll check the whole of the second word with the prefix of the first. We'll check these two cases, and we'll take whichever one gives the maximum. We'll continue this way, always comparing the last two letters. It's important to note that in all the three cases, we're always shortening the string in some way. In the first case, both strings get shortened. In the second case, only the second string gets shortened, and in the third case, only the first string gets shortened. But at least they're slowly but surely getting smaller, and we know that eventually we'll get down to our base case. By the way, what is the base case here? The length of an empty string is 0, and that's what we'll return in our base case. Now, let's get down to writing the algorithm. Let's write it up as a recurrence relation, because once we have that, we're as good as done. First, some definitions. X and Y are the two words we're comparing. X sub I is the prefix, the first I letters of X, and the same for Y, using J as an index. Y sub J are the first J letters of Y. Some examples for the words we have, happiness and pinecones, are X sub 1 is H, X sub 3 is HAP, Y sub 4 is PINE, and Y sub 9 is the whole word. Okay, so we're ready to write the recurrence relation to get the length of the longest common subsequence between two sequences with length I and J. The relation is nested, so we'll build it up case by case. Let's start with the base case. When I or J is 0, that means one of the prefixes is empty. So we'll return 0 because empty strings have 0 in common with other strings. Now for the case when neither I nor J are 0. Actually, this splits into two cases, when the last letters match and when they don't. Starting with when the last letters do match. Here we add 1 to our count and recursively examine both words shortened by one letter. Now for the case where the last letters do not match. Remember, here we checked the prefixes in two ways, also recursively, and we took the maximum. So we're going to do that here. We'll call LCS recursively on the whole of x and a prefix of y. And then we'll call it on the whole of y and a prefix of x. So that's it basically. You have the recurrence relation, and now you can implement a recursive algorithm straight from this formula. The algorithm will run in exponential time, so we will still need to memorize it. But this is the core of a correct algorithm to find the length of the longest common subsequence between any two strings. Congratulations!